Friends, from today we start the new series of the organic chem reaction, in which first reaction is Birch reduction. Generally, in chemical methods of the reduction reductions, the reductions are the two types. It is first one is the addition of electron to the unsaturated compound, followed by transfer of protons. It is simply addition of the electrons to the unsaturated compound followed by transfer of protons, in which the source of the electrons is metal like lithium, sodium, potassium, and followed by the abstraction of the proton from the proton donor like the ethanol, acid, or water. And second category of the reduction is addition of the hydride ion by addition of hydride ion. These are the two main categories of the reductions in chemical method of the reductions. There are two categories. Okay, so now our Birch reductions is in first category, that is the reductions involving the electrons, that is the addition of electron to the unsaturated compound. So in Birch reduction we use solvated electrons. It can generate like this one: lithium in liquid ammonia gives lithium cation along with electrons. Is the reactions, and these solvated electrons, because of the solvated electrons, the color of the solution is blue color. And this solitary electrons also react with the slowly with another molecule of the ammonia electrons and gives NH2 minus plus half of the H2 molecules. But this reaction is very slow, so we use this blue color solutions for the Birch reductions, or solitary electrons for the Birch reductions. Now we start the first category of the Birch reductions, that is the reduction of the reduction of aromatic compound. Reduction of aromatic compound involves two types. That is, first one is aromatic compound. Suppose benzene having a electron donating groups, and second one is benzene having the electron withdrawing groups. On Birch reduction, that is a lithium in liquid ammonia in ethanol solvent, and second one is again lithium liquid ammonia in ethanol solvent. So depending on the groups, that is electron donating or withdrawing, the Birch reductions varies like this. For the electron donating groups, the Birch reductions goes to the ortho and meta positions. So double bond is here. And for the electron withdrawing groups, it reduces the ipso para position in case of the electron withdrawing group. Now we see the list of the electron donating and electron withdrawing group. Electron donating group is equal to like OH group, OR, SR, NR2, aldehyde, ester, or etc. Okay, and now in your question arises in your mind that why I can write the electron donating group category aldehyde and ester. Now in case of the Birch reductions of the aromatic compound, the in aromatic aldehyde or ester, first reduce the carbonyl group of the aldehyde or esters, it convert to the corresponding uh, allylic alcohol anion like this anion, and this anion act as a electron donating group. So right here there is a CHO and COR. Okay, then electron withdrawing group for the second one. This first category, this is the second category. There is electron withdrawing groups, aromatic ring having the electron withdrawing groups. For example, COH group, C double bond O, NH2 group, amide groups, etc. In such case, the reduction happen at the ipso and para position. So you can write this as for electron donating groups present, it is the ortho meta directing for Birch reductions, or simply Birch reduction happen at the ortho and meta positions in case of the electron donating groups, or in case of the electron withdrawing groups, Birch reductions at ipso and para position. We see by the mechanism. First, see the mechanism of the electron donating groups. We take an example of the OMe on which Birch reduction, sodium in liquid ammonia in ethanol solvent. So we write the mechanism by step. We can also take a sodium in liquid ammonia or lithium in liquid ammonia. So we see earlier that the solitary electrons attack on the meta position of the anisole. Question arises in your mind that the why meta position first attack and the meta position, because of the OMe group is the electron donating groups and it having the much more electron density at the para position as well as ortho position, but it's electron deficient at the meta position. So by the site for the attack of the electron is suitable at the meta positions and not at the para position or ortho position, or it can stabilize the negative charge at the ortho position because it having the lesser electron density compared to the para positions. So we get like this. Here is one proton is there present. So this anion, radical anion, this is a radical anion, abstract the proton from solvent like ethanol. Let's abstract the proton from the ethanol, and we get the next first one proton is there, and abstract the second proton from the OMA group. Okay, once again the second electrons from second solitary electrons add at the meta position, and we get here negative charge. First proton is there. After that, this anion abstract the proton from solvent or ethanol. Sorry, OH. Abstract the proton from the solvent, and we get the final product. So that's why we can say that ortho and meta position reduces in case of the electron donating groups. Now see the mechanism for the aromatic ring containing or attached to the electron withdrawing groups. Same here, that is a condition. Sodium in liquid ammonia and ethanol as a solvent. Now see the step-by-step mechanism for electron withdrawing groups. Now here electron withdrawing groups withdraw the electron density much more from para position and ortho positions. It is electron rich at the meta position, so we cannot add like the electron add electrons at major position. We add the electrons at the para position because it is a electron deficient position for the electron withdrawing groups. So we get it can stabilize the negative charge at ipso position. Ipso position means the substituent attached to the position. These are functional groups attached to the position. That is the ipso position. Okay, this is the ipso position. This is the ipso position. Ipso position. Okay. Now in our mechanism we get C double bond O, OH, negative charge here, double bond. Here proton is already present, is the electrons. Now again this negative charge also in conjugation with the carbonyl. Okay, then in next steps it abstract the protons from the solvent. We get the reduction at the ipso position. Now further addition of the electrons, that is the solitary electrons at para positions. We get anion to the para position. Sorry. Okay. And it is the anion at the para position. It abstracts the protons from solvent. It's like this. Here we get the final product. So it is an ipso and para position reduction happen. Here ipso and para position reduction happen. Now we see the example by which we can understand the Birch reduction involving the electron withdrawings and donating groups. Lithium in liquid ammonia. It's a solvent ethanol. Now this is the methyl groups, CH3 and CH3. We know that the alkyl group is the electron donating groups. So by considering this methyl group, the possibility of the reduction happen at ortho to these groups and meta to these groups, and also with respect to these methyl groups, the reduction happen at the ortho to these groups and meta to these groups. So get the product like this. Okay, now we take another example. Here is a methyl groups, here is a OMe groups. Both are the electron donating groups. Lithium in liquid ammonia, ethanol solvent. So it is a more electron donating groups is the OMe groups as compared to methyl groups. So first consider the with respect to OMe group. Here is ortho position, and this one is the meta positions. Or by considering this ortho position, this is meta position. So reduction happen at this position, that is this one, this one. By considering the OMe groups, and also consider the methyl groups. It is this is also ortho position of the methyl groups and meta position for the methyl groups. So reduction happen like this. It reduces the ortho and meta position with respect to both the groups. Okay, then we move towards the next category of the Birch reduction of the aromatic compound. Is the Birch reduction of bicyclic aromatic compound. We know the famous example. Okay, then our condition lithium in liquid ammonia and ethanol solvent. Okay, so now there are two rings, two aromatic rings, that is this one and this one. So in such a case, that is a reduction for the Birch reduction of the bicyclic aromatic compound, we reduce the electron deficient ring with respect to electron rich rings or compared to the electron rich ring. In any case, that is for the electron donating groups or electron withdrawing groups present on the rings, we reduce first the electron deficient ring. Electron deficient ring readings reduce only. Okay, so in this example, this is the electron rich ring because of the two methyl groups. So reduction happen for this ring only, and this is the intact. Okay, we take another example. in liquid ammonia and ethanol as a solvent. Now in this case, electron withdrawing group present in these rings, so this ring is reduced, because as we know that in a Birch reduction we add the electrons, and electron addition is possible in the electron deficient centers and not in the electron rich center. So the electron deficient ring is reduced. We get the product. COH groups. Okay. So we note here that for the bicyclic system, for bicyclic aromatic compound electron deficient ring reduced. Okay. Now in three parts, that is we see the reductions of the aromatic compound having the electron withdrawing groups, having the electron donating groups, and in case of the bicyclic compound. Now we move towards the Birch reduction. Birch reduction of enone, or simply Birch reduction of alpha beta unsaturated ketone. Okay, we'll take an example. So, lithium in liquid ammonia, ethanol as a solvent. Okay, now in case of the alpha beta unsaturated ketones or the enones, the Birch reduction happen only at the alpha beta unsaturated centers and not reduce the carbonyl centers. Okay, so we get the product like this one. Only the alpha beta unsaturated system is reduced and not the carbonyl center. This is not reduced, only this one is reduced. Okay, we see the mechanism step by steps. So there is solvable electrons present in the liquid ammonia attack here. We get this way. This one again, it abstracts the proton from the solvent, that is ethanol. We get the OH double bond is the anion. This anion further take solid electrons, solid electron add like this one. We get the next structure. Sorry, sorry for that, it happened by mistakenly. We see in the next page. This okay, we are here. Okay, then second electrons add to this position, we get the anion. This anion abstract proton from the solvent. So we get the final product like this one. We just simply write this the keto form of these groups. Is a keto form of the group. Okay, it's the extraction proton. So in case of the alpha beta unsaturated systems, only carbon group is intact and only reduce the alpha beta unsaturated systems. So now we move towards the reduction of alkyne. It is the Birch reduction of alkyne. Birch reduction of the alkyne. Now general reaction. Lithium in liquid ammonia. Now in this case, on the Birch reduction of the alkynes gives transalkene. We see the mechanism for this reaction. First of all, solid electrons add to this positions. We get the radical anion. This radical anion abstract the proton from ammonia. This is the here in this case the in a reduction of the in Birch reduction of the alkynes, there is no need of the alcohol as a solvent, because this is the enough basic to abstract the proton from the ammonia. So we write here like this. Again solid electrons add to this position and we get vinyl anion. This is the unstable in the cis position, so it is move towards the trans position like this one and get the stability. Again it abstract the proton from solvent and we get the trans product. So on the Birch reductions of the alkyne, we get always trans product or transalkene. Now in the next lecture we see the previous year example on the Birch reductions from GATE, NET and the IIT-JAM exams. So we can stop here. Thank you for watching the video.